everyone see slides?
I do.
Okay, perfect. Okay, so I'm gonna start. So the talk is about 3D frame field integrability and more specifically through branches scaling. So first of all, for a bit of context, 3D frame fields are used as a tool for building X dominant meshes and full X meshes of 3D domains. The fact is that all the methods used are dealing directly or indirectly with the fact that the frame field is integrable or not. So the question we want to answer is if we are given a 3D domain omega and a unitary 3D frame field on this domain, is it possible to make it integrable only by scaling its branches? To answer to this question, I'm going to follow this outline. So first, I'm going to present integrability equations and how we obtain them. Then show some result with this scaled frame field. And then finally talk about a specific integrability condition. For integrability equations, we will need a few definitions. We are going to call a frame a set of three non-unitary orthogonal vectors that I called here U tilde, V tilde, and W tilde. To represent these three vectors, we need 6 parameters. We have chosen like 3 of them to represent the norm of the vectors. They are called here HL, HM, and HN. And we can then represent orientation of these vectors with, for example, 3 Euler angles. So I put on top the expression of the normalized vectors UV and W with 3 Euler angle, psi, theta, and phi. The next tool we will need is the Lie bracket to define integrability. So if we have 2 given vector fields U tilde and V tilde, they are integrable if and only if their Lie bracket is equal to 0. For those who are not familiar with this, I'm explaining it on a small 2D example on the left. We are given 2 vector fields U and V, and we are going to generate 2 points starting from the point P. By following the blue path, doing 1 step among V and then 1 step among U, we are generating the first point. And by following the green path, doing 1 step among U and 1 step among V, generating a second point. And the Lie bracket is equal to 0 if these 2 points are the same. So here we can see that if we are supposing the orientation of vectors fixed, it is possible to make these 2 points to be the same by playing on the size of the steps, which is basically playing on the norm of the vectors. So it's what we are going to do for a 3D frame. So we are dealing with 3 vector fields, and we are just going to write the Lie bracket for every possible couple of these vector fields. So for U tilde, V tilde, U tilde, W tilde, and V tilde, W tilde. This gives us 9 scalar equations. And among these equations, 6 are involving the scaling factors HL, HM, and HN. We have 3 other equations that I'm going to talk about later in this presentation. So to have a closer look at these equations we are obtaining, I put here only the one involving HL, but it's basically the same for all scaling factors. We can first notice that they are linear regarding the scaling factors because there are equations on their covariant derivatives. And these derivatives are only depending on the frame field orientation, which is known. like the three fields psi, theta, and phi are known. We can also notice that it's not a well-posed problem. The gradient of HL is not totally defined. We're missing some informations. What does it tell us is that we have like an infinity of solution. And by infinity of solution, I mean that the space of solution can be of infinite dimension. So to solve this, we will need to regularize the problem. So to explain how to do it, I'm just going to use a 2D example because it's a bit more simple to explain. So we are going to suppose a rectangular domain omega. And we are looking for a scalar function h, such as the gradient of h among y is equal to g, a given function. The g doesn't really matter here. I put one example and a plot of its value on the domain. We can use like a first naive approach to try to solve it by using regular solvers. If we are lucky, they can converge to a minimum. So it's the case here, but it's not guaranteed at all. So here we are seeing that when we try to solve this problem with a conjugate gradient, we are getting the solution on the left. With a GEMRES, the solution on the right. The thing is that both are very slow to converge, it's expected. These are two very different solutions, and they are both acceptable. Like they are all matching the condition on the gradient of h among y. So we need to regularize this, first to be able to all the time solve the problem, if possible to accelerate it, and to limit the search to a unique solution. So the idea is we are going to call our objective function, our cost function E, which is basically just the norm of the gradient among y of f minus g. And we are calling S our space of solution. And to limit the search to only one solution, we are saying that we want to grab the solution in S, which has the smallest gradient norm. How to do this? So first we can notice that we are transforming our linear problem into a non-linear one this time. To do this, we are starting from an initial guess, which is 0 on the whole domain. And then iteratively, we are going to compute new solutions by minimizing our cost function E plus a penalty on the gradient in the direction which is unknown. In our case, it's x. And for this penalty, we are going to take the value of the precedent solution. And we are iterating until we have reached a minimum. And this works actually very well. Here is the regularized solution we are getting. So the advantage is first that we are looking for one solution, and then it's the scaling factors are linked to the dimension of hexahedras we are going to generate. So the fact that we are looking for scaling factors with the smallest gradient possible is actually what we could be looking for when generating X meshes. But nothing forbids us to put other kind of conditions. And this is exactly what method we applied to solve the 3D equations on the 3 different scaling factors. So here I'm going to show some results. The first one is just a plot of the potentials we are obtaining after having scaled these 3 vector fields. So I tried to make a rendering to show that the ISO values we are getting are actually following well the cross field, but it has proven to be hard, and I haven't managed to make something very understandable on a picture. So you will have to take my word for it. But we are getting nice ISO values. But of course, as people working on the parameterizations problem, it's not enough by itself to generate a proper X mesh. Like we are still very dependent on how clean the cut graph is, and more important, nothing ensures that ISO values are matching across a clean cut graph. The second result I'm showing is actually the purpose for which this scaling has been developed. So Christos presented this morning a method to generate X-dominant meshes with point generation. And this point generation is guided by a 3D crossfield. Beforehand, it was done with like a unitary 3D frame field. And we can see that on the picture on the left, that a lot of non-X elements are generated in areas where the crossfield is turning a lot. On the pictures, all white elements are hexahedrons, and the ones which are colored are others, like prisms, pyramids, tetrahedrons, etc. On the right, we can see the mesh generated following the exact same method, and all elements, non-X element generated because of the non-integrability of the crossfield disappeared. We can see it like in areas where the crossfield is turning a lot are quite clean now. The only one left are due to the method used. So this shows that the scaling the crosses in these cases are quite good to make them integrable. But now we are going to talk about a more specific problem. I told you there were like a set of 9 equations, and only 6 were involving the scaling factors. And there are 3 equations left. So as people working on frame fields are well aware of, there are some cases where when computing a 3D frame field, the singularity graph we are getting is not matching any doable X mesh. So this one is like a famous example, but there are many other of them. So if we get a look of the 3 last equations that I put here, they are not involving at all scaling factors and only the crossfield orientation. To better understand them, we can put ourselves in a very specific case and suppose a frame field with one direction which is always constant. Here it's going to be W tilde, and which is always aligned with the vector Z. Our crossfield can be represented only with one angle phi, which is here depending on X, Y, and Z. If we are using the 3 equations above, what we can get from it is that phi, in order for the crossfield to be integrable, has to depend only on X and Y. So we can see it actually quite easily on the picture. If we are starting from this point, following the blue path by doing one step among W and one step among U, and then doing the same thing on the green path, one step among U and then one among W, we see that whatever step size we are taking, it will be impossible for these 2 points to be the same if phi depends on Z. So to compute an integrable 3D frame field, we have to be sure that these 3 equations are ensured. And it's not the case with current ways of computing frame fields. Everything rely, so there are different ways to do it, but rely or on smoothing the Laplacian of a cross representation, or many other ways, but none are actually trying to respect this. And that's why we are getting this kind of cases appearing, like non-meshable singular graphs. We are currently trying to find a solution to compute cross-field fitting these three equations, but for now we don't have any solution. And that's it for me. If you have any questions.
So, oh, okay. So, anybody has questions?
Yeah, I have one. You mentioned that you had problems with the cut graphs, that you did not consider consistency there, and that then the result depended on the cut graph. Where does it come from? Are the kind of transition functions for these equations too complicated, or what is the issue here?
Oh no, the issue at cut graph. Sorry. So here, so it was just to look at the sheets if they were well aligned with the cross field. So when computing this, the only thing we are seeing is that there is discontinuity at the cut graph, but we are not adding any other conditions. Like it was a very rough computation to see if we are actually following the crosses. I don't know if it answers the question or not at all.
Yeah, no, thanks for clarification. I misunderstood it.